it's way too early in the morning, and I want to go over this analysis tools for algorithms and data structure, so I'm gonna whisper for just this video, okay? Just this video. I'm gonna stop whispering. Alright, so we're gonna go over 7 functions that are used in this book, analysis of algorithms, and how to justify using induction. Okay, but before I begin, there's something is wrong with my code. Okay, I spent the whole day yesterday trying to figure out for this, making this generic simple linked list in C++, but for some reason it's not working. I just keep getting compiled errors, so I don't know why it's not working. So if you guys could figure it out, please help me, because I'm trying to finish that other video about getting finish all the recursive problems in the other video. So here I'm gonna show you the chapter 3 of C++ of my problem for a singly linked list. It's just a generic singly linked list. I don't know why I keep getting these debug errors, these really bad errors. Okay, I'll just show you what it is. Okay, this is the singly linked list header file that I have. It's just generic linked list with template. I include the node.h, and it's a class that has all these things: empty constructor, destructor, empty front, add front, remove front. Okay, and if a node, I make it a generic, right? Here, the header list. Okay, and here is the singly linked list node. Okay, I made a friend for class of s linked list so that s linked list can have access to element and of next. Okay, so I did that. Okay, it's private. Okay, so I did that. Okay, and here's my singly linked list.cpp. Okay, it's just implementation file for this. Okay, this is the constructor. Okay, this is the destructor. While it's not empty, I remove the front. Okay, I include singly linked list.h. Okay, and here's the linked list for checking if it's empty. Okay, and here's the adding to the front. Okay, not adding to the front. This is a constant value that returns a value at the front. Okay, and then here's the add to the front. Okay, it just adds to the front link list to the node to the front of the link list. Okay, so here's remove from the front. Okay, that's all it does. Okay, and for some reason, please help me. I don't understand why this keeps getting compile errors. Look, it keeps saying syntax error. I don't get why. I'm just having friend class of s linked list. Okay, I just don't understand. And it keeps saying this has been declared as already as a non-class template. I keep getting all these strange errors. I don't know what this is. So please help me on this one, by the way, because I don't understand why this is not working. Okay, and this destructor tag, this is the same. I'm doing it correctly. Okay, I'm doing it correctly. I put the tilde and I put everything. I don't understand why this is not working. I'm literally completely stuck at this point. Look at this. It's the right tilde. They're both right. It's the same name as a destructor. I don't get why I'm having that compile error of a tilde sign right here. Destructor mismatch. That's not true though. I'm design destructor mismatch. Okay. Alright, that's what I'm saying. Okay. Okay, now that we settled that, please help me on this one. And now I could go over the 7 functions and analysis of algorithms. So okay, so let's go over this now. So what are the 7 functions used in this book? So in this book we discuss 7 most commonly used functions in analysis of algorithms. We use only of these 7 functions for almost all the analysis we do in the book. In fact, sections that use a function other than one of these 7 are marked with a star to indicate that they are optional. In addition to these 7 functions, they contain other mathematical facts that apply for data structure and algorithms analysis. Okay, so the first function that we're going to go over is the simplest function we could think of as a constant function. And this function, for some fixed constant c, it's just c equals to 5, and c equals to 27, or c equals 2 to 10. That's for any argument n, the constant function assigns a value c. Otherwise, it doesn't matter what the value n is. if n is always greater than the constant c. Since we have the most interest in integer functions, the most common function to the constant is g of n equal 1. This is a typical constant function, and we use this in the book. And note that, like any other constant function, f of n equals c can be written as a constant times c times g of n. Thus, f of n can equal c times g of n. This is just saying that functions can be written as other functions times other functions. Okay, as simple as it is. Constant function is useful in algorithms because it characterizes the number of steps it needs to do basic operations on functions, and also on computers, like adding two numbers and assigning a value to some number or comparing two numbers. Okay, we're going to go over logarithm function. One of the most basic and interesting things called logarithm of functions is when f of n equals the log base b of n for some constant b greater than 1. This function is defined as x equals log of b of n if and only if b of x is equal to n. So log base b of 1 equals 0. The value of b is known as the base of the logarithm. Okay? Because that's because b of 0 is equal to 1. Okay? I mean b of 1. Yeah, b of 0 is equal to 1. That's the reason why log base b of 1 equals 0. Okay, now computing the logarithm function exactly for any integer n involves the use of calculus, but we use an approximation that's good enough for our progress without calculus. In particular, we can easily compute the smallest integer greater than or equal to log a of n. Since this number is equal to the number of times we can divide n by a until we get a number less than or equal to a. For example, the evaluation of log 3 of 27 is 3. Since 27 divided by 3 divided by 3 divided by 3 equals 1, this evaluation is log base of 464 is 3. Since 64 divided by 64 divided by 64 divided by 64 is equal to 1, the approximation of log base 2 of 12 is 4, because 12 divided by 2 divided by 2 divided by 2 divided by 2 is equals 0.75. Okay, which is less than or equal to 1. The base 2 approximation arises in algorithm analysis since common operations in many algorithms is to be repeatedly divide an input in half. Alright. Some computers may store integers in binary, but most common base for logarithm function in computer science is 2. This is because the base is so common that they normally leave it off. So when we don't consider the base, we actually mean base 2. Okay, guys? Alright, so here's some most handheld calculators have a mark button log, but they're calculating base 10, not base 2. Alright, so here are some rules in log functions. When a is greater than b, a is equal to 0, b is greater than 1. My bad, if a is greater than 0, b is greater than 1, c is greater than 0, and d is greater than 1. When you have log base b of a, c, you could add them separately. Okay? When you have log base b of a divided by c, you can subtract them separately. If you have log base of b, a to the c power, you could take the power in front of, put it in front of log base b. If you have log base b of a, you could actually divide log base a divided by log base b and change the value of the base. You could do that because it doesn't matter the base at that point. If you have if you have b to the log of d base a, okay, that's very strange, okay? And you could actually switch it with the base and the whatever number on this top. So you could have a to the log base d of b. So here's a notation we shorthand. When we use log to the c power of n, we actually mean log of n to the c power, okay? Here's what they're doing in the book. So rather than showing how we derive the identities to show the definition of logarithms and exponents, they'll illustrate these identities instead. So here they put, here are all the, they add different numbers. What they're doing here, a log of 2, a log of n, and all this stuff, that's what they're doing here. As a practical matter, none with our root 4 gives us a way to compute base 2 on a logarithm calculator. It has base 10 logarithm button. So 1, 2, 3, 4. Basically it's saying log base 2 of n. You could change to whatever log base 10, whatever base it is, divided by log base of this number, right? Your old base. So you could say log base of 2 of n is actually equal to log base 10 of n divided by log base 2. That's what they're saying in rule 4. 1, 2, 3, 4. Is this one? I don't think they should say rule 4. They should say rule... Yeah, rule 4. That's what they're saying. Okay. Okay. Next, as a function, we have a linear function. When f of n equals to n, is it given an input n, the linear function assigns the value n to itself. This function arises anytime we do single base operations for n elements. For example, if we compare x to each of the elements in size of n, that requires n comparisons. The linear function also represents the best running time we could hope to achieve for any algorithm that processes a collection of n objects that are not already in the computer's memory. Just start reassigning. Since reading in the n objects itself requires n operations. Okay, now we're going to talk about n log n. Next function they describe as n log n. The function assigns an input n to the value of n times the logarithm of base 2 of n. This function grows faster than the linear function and a lot slower than the quadratic function. Thus, on general, on several purposes, if we can improve the running time of solving some problem from quadratic to n log n, we have an algorithm that runs much faster in general. Right, here's another one. Quadratic function f of n equals n squared. Another function that appears a lot in algorithms is quadratic functions. That is, given an input value of n, the function f assigns the product of n with itself, meaning n squared. The main reason why the quadratic function appears in analysis of algorithms is that there are many algorithms that have nested loops, where the outer loop performs the same number of operations as the inner loop. Okay, so that's what this one, you have 2 for loops, and they both run up to n times, so that's why the algorithm performs n times n. Okay, so nested loops and quadratic function. The quadratic function can also arise in the context of nested loops, where the first iteration of the loop uses 1 operation, the second uses 2 operations, and the third uses 3. The number of operations is then 1 plus 2 plus 3, going up to n minus 2 plus n minus 1 plus n. So what does that mean? That means the total number of operations that are performed by the nested loop. If the number of operations performed inside the loop increases by 1 with each iteration of the outer loop. So one instance is like if you loop through from 0 to n, and I'm guessing you, instead of looping from 0 to n, you do from like x equals to x, j equals to x plus 1, you're looping that to the end. I'm guessing that's what they mean. So this is the total number of operations that are performed by the nested loop. The number of operations performed inside by the loop increases 1 with each iteration of the outer loop. This quantity has an interesting history. So the German school teacher decided to keep 9-year-olds occupied by adding up numbers from 1 to 100. Almost immediately, one children claimed to have finished the answer. The teacher was surprised. The only way to do it, his answer was correct, so he grew up being one of the famous mathematicians. His name is Gauss. Okay, so here's a proposition for any integer. N is greater than or equal 1. We have 1 plus 2 plus 3 plus 4 up to n minus 2 plus n minus 1 plus n. That's actually equal to n times n plus 1 over 2. You guys might have learned this in grade school or in high school, I don't know. Somewhere you learned it, but that's basically what it is saying. Here's the justification. If you graph this line on n and n, you could actually take all these triangles and rearrange it to the other side. So you get n plus 1 times n over 2. Okay? It's very strange, but okay. So here's the visualization. In terms of the total area covered by n unit with rectangles with heights 1, 2 up to n. In A, the rectangles are shown to cover a big triangle of area n squared over 2 plus a small triangle of 1/2 each base 1 and height 1. In base, in B, it implies that only when n is even, the rectangles are shown to cover a I'm having a brain headache. Okay, so that was a lesson of there. So the lesson you learned from proposition of 4.3 is that if we perform an algorithm with nested loops, such that the operations in the inner loop increase 1 each time, then the number of operations is quadratic in the number of times n we perform on the outer loop. In particular, the number of operations n squared over 2 plus n squared plus n over 2. In this case, which is a little more than a constant factor of 1/2 times a quadratic function n squared. In other words, such an algorithm is only slightly better than an algorithm that uses n operations each time the inner loop is performed. Okay. Okay, now let's talk about cubic functions and other polynomials. So, another thing that we do is something called the cubic functions, which assigns an input value and the product of n times itself 3 times. This function appears less frequently in a context of algorithm analysis than the constant linear and quadratic function, but it does appear from time to time. Polynomials. Interesting. The functions that we have listed so far can be viewed as being part of a larger class of functions called polynomials. The polynomial is a function of the form fn equals a0 plus a1 times n plus a2 times n squared plus a3 times n cubed plus all the way up to a of d n to the d power. Okay, so what do they mean by this? It's just like any polynomial. It's just a definition of the polynomial. A0 to a up to ad are just random constants of the polynomial, and they don't really matter. But ad can't equal 0 because the highest power cannot be 0. Why? Because then it indicates the highest power of the polynomial, right? So if ad does equal to 0, then that's not the highest power of the polynomial. Because they're just defining it that it can't be 0 because they want the highest power of the polynomial to not have the first coefficient be 0, right? So integer gd, which indicates the highest power of the polynomial, is called the degree of the polynomial. So for example, the following functions are all polynomials. 2 plus 5n plus n squared. F of n equals 1 plus n cubed. F of n equals 1. F of n equals n. F of n equals n squared. So therefore, we could argue that this book represents just 4 important functions used in algorithm analysis. But we stick to just saying that there are 7 since the constant linear and quadratic functions are too important to be lumped in with other polynomials. Running times that are polynomials with degree d are generally better than polynomial running times with larger degree. So let's talk about summations. Another thing we use in data structures is summing things up. This is defined as this weird thingy. That's a sigma notation. Okay, so you get I equals a to b of f of I. What that means is you keep adding up everything. You plug in the function of a into this f of I, right? And you keep adding it. A plus 1, a plus 2, right? This function at the value a plus the function at the value a plus 1 plus the function at the value a plus 2 up to f of b, where a, b are integers and a is less than or equal to b. Summations arise in data structures and algorithms because the running time loops naturally give rise to summations. So using summations, we could derive the formula, the proposition that we saw before as the summation of I to the n of I is equal to n times n plus 1 over 2. Likewise, we could write the polynomial f of n of degree coefficients as the summation of I equals 0 up to d of a of I times n to the I power. Thus, summation notation gives a shorthand way of expressing sums increasing terms that have regular structures. Let's talk about the exponent function. Alright, another function we use in analysis of algorithms is the exponent functions, where b is a positive constant called the base, and the argument n is the exponent. So instead of, remember before, the exponent, the logarithm function was another thing with log base b of n. Well, this is the difference. This is the exponent function, where it's f of n equal to b to the n. Okay, so b is a positive constant called the base. Argument n is just the exponent. That is the function f of n assigns the input argument n, the value obtained by multiplying the base b by itself n times. In algorithm analysis, the most common base for the function is b equal to. For instance, we have a loop that starts by performing one operation operations performed with each iteration than the number of operations performed in the nth iteration is 2 to the n. In addition, an integer word containing n bits can represent all the non-negative integers less than 2 to the n. Thus, the exponential function with base 2 is quite common. The exponential function is also referred to as a exponent function. We sometimes have other exponents besides n. However, it is also useful to know that there are a handful use rules for working with exponents. In particular, the exponent rules are very helpful. So you take an exponent, raise it to another exponent, and then you raise it to another power. When you take a base b and raise it to an exponent and raise it to a c, you get b equals to 8. You can multiply the exponents together. Okay? We have a base exponent of a base b raised to a times exponent of base b raised to c. You can add them together. And if you divide 2, you could subtract them together. And here's an example that they have here. Okay? You can extend the exponent function to exponents that are functions or real numbers or negative exponents as follows. Given a positive integer k, we can define b1 over k to be the kth root of b. That is a number r such that r to k equal to b. Yeah. So that what they're saying is b to the 1 over k is the kth root of b. So r to the k can equal b. Okay. The number r is such that r to the k equal to b, and r represents the kth root of b. For example, 25 to the 1/2 power is 5, since 5 to the 2nd power equals to 25. Okay? All they're saying is that you could change this number to be this number when you raise it, okay? So 25 to the 1/2 power equals 5. That means 5 to the 2nd power equals to 25. Likewise, so 27 to the 1/3 power equals 3. 3 to the 3rd power equals to 27. Alright, all they're saying here, 16 to the 1/4 power equals 2. You could say that means 2 is to the 4th power is equal to 16. That's all they're saying here. Okay, this allows you to define the power of exponents, representing them as fractions, using this rule. Thus, b to the a over c is really just the cth root of the b of a. Okay? So you can also extend exponent functions to define b of x for any real number, integer x, by computing a series of numbers of the form b to the a over c for fractions, a over c that get progressively closer and closer to x. Any real number x can be approximated close to the fraction a over c. Hence, we could use the fraction a over c as an exponent to get close to the other b, to get close to b to the x. Okay, so they're saying the number 2 to pi is well defined. That's what they're saying. Okay, but finally they could also do a negative exponent d, such that you could define b to d equals actually the 1 over b to negative d. This is just saying the power of the exponent. So like if you do 2 to the negative 2 power, that's actually 1 over 2 to the 2 power, right? Right? If you guys remember. That's actually what it is, okay? So like b to the negative 2 power is actually equal to 1 over b to the 2nd power. Okay? Think about that. That's what this is representing, which corresponds to the exponent rule of 3. If you set a equals 0 and c equals negative d. Alright, let's talk about geometric sums. So, suppose a loop where each iteration takes a multiple factor longer than the previous one. The loop can be analyzed using the following proposition. For any integer n is greater than or equal to n0, any number a such that a is greater than 0 and a is not equal to 1, consider the summation. All they're doing here is they're summing up the values ai for starting I equals 0 up to n, okay? So they're saying this time they're summing up the exponent values, okay? Yeah. The geometric summation, they're changing the value of the exponent this is a geometric sum now. So remember that a is 0 is equal to 1. If a is greater than 0, the summation is also equal to a to n plus 1 minus 1 over a minus 1. Summations are also called geometric summations because each term is larger than the previous one. So if anyone working in computing should know that. 1 plus 2 plus 4 plus 8 up to 2 to the n minus 1 is actually equal to 2 to the n minus 1. Okay? Since this is a large integer that could be represented in binary notation of n bits. Okay, so people working in computing probably memorize this because it represents the largest integer you could represent in binary notation using n bits. I don't know why anyone would memorize this, but okay, that's good information to know. Alright, let's compare growth rates right now. Let me just do something. Okay, let's talk about growth rates. So to sum up, here are the 7 common functions we used in the book, where we just review the constant, the logarithm, the linear, the n log n, which is the constant times the logarithm, the quadratic, which is n squared, the cubic, and the exponential. So ideally we like the data structure to run in times proportional to the constant. Like we want the data structure to be constant, okay? Because we would like our algorithms to run in linear, or n log n time. Reason why is because these are really fast. Okay, if your algorithm runs at these times, that means it's very fast. Okay, normally you don't want the ones on these ends. Okay, so algorithms quadratic or cubic are less practical, but algorithms of exponential running times are infeasible for small inputs. So here they graph the time of all these functions. Okay, this is the cubic. Alright, this is cubic function. This is the exponential function. Wait, look at that. That's rises to the top quickly. It's kind of inefficient. Okay, here's a quadratic, which is also kind of inefficient. And log n is pretty efficient. Okay, that's a square. The square ones is n log n. Look at it. It just rises a little. It's faster than the quadratic because it doesn't increase its slope that quickly. See, look at that. Alright. Now here is the linear, which is here is linear, so it's lower than the thing. Okay, linear. Which is faster. You want it to be linear. And then here's the constant, which is at 0. They made the constant at 0. And the logarithm, you want it to be logarithm as well. Look at the n log of n. You want that. You know why? Because that is very fast. We also want it to be like constant, which is very fast. Alright, the growth rates for several functions used in algorithm analysis. We use base of a equal to for exponential function because the functions are plotted in a log chart to compare the growth rates primarily as slopes. So the algorithm function grows too fast to display all of its elements in the chart. See, that shows that the exponent function grows too fast. That means it's not efficient, okay? Alright, now we're going to talk about flooring and ceiling. So in addition, the comment concerning the functions above is in order the value of an logarithm is typically not an integer, yet the running time of an algorithm is usually expressed by means of an integer quantity, such as the number of operations performed. The analysis of an algorithm may sometimes involve the use of a floor function and a ceiling function, which are defined respectively as follows. Okay, here's the floor function, largest integer less than or equal to x. Okay, so I'm guessing, so like if you have 3.14, largest integer less than or equal to x, the floor would be 3. Okay, you're just rounding downwards. Okay, so smallest integer greater than or equal to x. So remember, 3.14, smallest integer greater than or equal to x is 4. So you're rounding upward, okay? Greater than, so that's what this ceiling. Ceiling is smallest integer greater than or equal to x, which you're rounding upwards. Floor function is the largest integer less than or equal to x, which is rounding downwards. That's just a way to remember it better, okay? Rounding down, rounding up, for floor, squiggly marks on the bottom and the squiggly marks on the top. Okay, let's go to the next one. Alright, so now we are at the analysis of algorithms part, which is, what this part, let's tell a story, a classic story. There's a mathematician named Archimedes who was determined if a golden crown commissioned by the king was actually pure gold and not silver. The informant had claimed. So what Archimedes discovered a way to perform this analysis by stepping in a bath. He noticed that the water spilled out of the bath in proportion to the amount of him went in. Realizing the implications of this, he immediately got out of the bath and ran naked throughout the city, shouting "Eureka!" For he had discovered an analysis tool displacement, which when combined with a simple scale could determine if the new king's crown was good or not. That is, Archimedes could dip the crown in an equal amount of weight of gold into a bowl of water to see if they both displace the same amount. This discovery is unfortunate for the goldsmith. However, for when Archimedes did this analysis, the crown displaced more water than a equal weighted lump of gold, indicating the crown was not in fact pure gold. So, in this book, we are really interested in the design of good data structures and algorithms. Simply put, a data structure is a systematic way of organizing and accessing data, and algorithms is a step-by-step procedure for performing some task in a finite amount of time. These concepts are central to computing, but to be able to classify some data structures and algorithms as good, we must have precise ways of analyzing them. So, the primary analysis tool we use in this book involves characterizing the running times of algorithms and data structures and operations, with the space usages also being of interest. So running time is actually a natural measure of goodness, since time is a precious resource. Okay, you want it to be as fast as possible. In general, the running time of an algorithm or data structure increases with an input size. So given like 1,000 elements, the time is going to increase. Processing 1,000 elements is going to increase, right? Although it also may vary for different inputs of the same size. The running time is affected by the hardware environment, also reflected by the processor, the clock rate, the memory, the disk, etc., and software environment as reflected in the operating system, the programming language, the compiler, and the interpreter, in which your algorithm is implemented, compiled, and executed. So all of the factors being equal, the running time of the same algorithm on the same input data is smaller if the computer has a much faster processor, or if the implementation is done on a program compiled into native code instead of interpreted implementation on virtual machines. It does, but regardless, nevertheless, in spite of the various variations of environment factors, such as the machine and the how fast the processes, we would like to focus on the relationship between the running time of an algorithm and the size of its input. So we are interested in characterizing algorithms running time as a function of the input size. But what is a proper way of measuring it? Well, what is the proper way of measuring an algorithm? Okay, so experimental studies. If an algorithm has been implemented, we can study its running time by executing it on various test inputs and recording the actual time spent in each execution. Fortunately, such measures can be taken in an accurate measure by using a system calls that built in the language by running the clock function that measures we're calling runtime environmental profile. Such tests assign a specific running time to a specific input size, but we are interested in determining the general dependency of running time on the size of the input. In order to determine this dependency, we should perform several experiments on many different test sizes of various sizes. Then we could visualize the results of the experiments by plotting them, the performance of each run of the algorithm as a point with x coordinate equal to the input size n and y coordinate equal to the running time t. So what they did was they used visualization in the data that supports it, and you could perform a statistical analysis that best fits the best function of the input size to the experimental data to be meaningful. This analysis requires that we choose good sample inputs and test enough of them to be able to make sound statistical claims about the algorithm's running time. Alright, so that's what they did here. They measured the input size n and then the time t milliseconds, and it allows you to make good statistical claims about an algorithm's running time. So while experimental studies of inputs can be done only based on limited amount of test inputs. You have a difficulty comparing the experimental running times of two algorithms unless the experiments were performed in the same hardware and software environment. And to fully implement and execute an algorithm in order to study its running time experimentally. So that's the reason why experimental studies of running times have limitations. Just running experiments have limitations. So the last statement is obvious, but it's probably the most time-consuming part of performing experiment analysis of an algorithm. The other limitations impose serious hurdles too. Thus, we would ideally like to have an analysis tool that allows us to avoid performing experiments. So now the rest of the chapter, we're going to develop a general way of analyzing the runtime of algorithms that takes into account all possible inputs, allows us to evaluate the relative efficiency of any two algorithms in a way that is independent from the hardware and software environment, and can be performed by studying a high-level description of the algorithm without actually implementing it or running experiments on it. So this method is at associating each algorithm a function of event that characterizes the running time of the algorithm as a function of the input size event. So normally functions that are encountered include the 7 functions mentioned earlier in this chapter. So here's some primitive operations. As noted above, experimental analysis is valuable but has limitations. If you want to analyze an algorithm without performing experiments on the running time, you can perform an analysis directly on the high-level pseudocode instead. So you could define a set of operations such as the following: assign a value, call a function, perform an arithmetic operations, comparing a number, indexing an array, following an object reference, returning from a function. Or these are operations, primitive operations. The code can run. So what we're doing now is counting the primitive operations. Specifically, a primitive operation corresponds to a low-level instruction with an execution time that is constant. Instead of trying to determine the specific execution time of each primitive operation, you can simply count how many primitive operations are executed and use this as a number t as a measurement of the running time of an algorithm. This operation count correlates to an actual running time in a specific computer. Since each primitive operation corresponds to a constant time instruction and there are only a fixed number of primitive operations, the implicit assumption in this approach is that the running times of different primitive operations are fairly similar. So thus, the number t of a primitive operation so an algorithm performs is proportional to the actual running time of that algorithm. So what they're doing is that they're basically counting the number of operations that each code does, right? And then they're assuming that the amount of time for each operation is similar on every single computer, right? So that's why they're able to use a function that allows you to correlate the time of how long it takes for that algorithm to run. So these operations are what they're counting. They're counting the operations, how long for each operation, and that basically allows them to create a function t measuring how amount of time it takes for the algorithm. Okay, so an algorithm may run faster on some inputs than it does on some others. Thus, we may wish to express the running time of an algorithm as a function of the input size obtained by taking the average over all possible inputs of the same size. Unfortunately, such an average case analysis is typically quite challenging. So, it requires us to find a probability distribution on the set of inputs, which is a difficult task. Here they're showing us how, depending on the input distribution, the running time of an algorithm can be anywhere between the worst case time and the best case time. So, what if inputs are really only of type A and D? So an algorithm can be between the best case time, which is here, and the worst case time. See, so what if inputs are really only of types A and D? They are only between the best case and the worst case. See, these are just running time, and then here, this is the average case to looking time for the rest of these algorithms. the worst case time. Each bar represents, here in the figure, the running time of some algorithms on different possible inputs. So, focusing on the worst case, an average case analysis usually requires that we calculate expected running times based on a given input distribution, which normally involves sophisticated probability theory. Therefore, for the remainder of this book, unless we specify otherwise, we characterize running times in terms of the worst case as a function of the input size and of the algorithm. Worst case analysis is much easier than average case analysis, as it requires only the ability to identify the worst case input, which is often simple. Also, this approach typically leads to better algorithms, making the standard of success for an algorithm to perform well in the worst case necessarily requires that it does well on every input. That is, designing for the worst case leads to stronger algorithm muscles, much like a track star who always practices by running up an incline. I don't get what you mean by track star, but basically we want to care about the worst case analysis because it's fairly simple. So, and it typically leads to better algorithms. So we're concentrating on worst case scenario right now. Alright, asymptotic notation. In general, each basic step in a pseudocode description or high-level language implements corresponds to a small number of primitive operations, like function calls, etc. Thus, we can perform a simple analysis of an algorithm written in pseudocode that examines the number of primitive operations executed up to a constant factor by pseudocode steps. So, in algorithm analysis, we focus on the growth rate of the running time as a function of the input size n. Okay, taking a bigger approach. So, it's often enough to just know that the running time of an algorithm, such as array max shown in the code, grows proportionally to n, with its true running time being n times a constant factor that depends on the specific computer. We analyze algorithms using a mathematical notation for functions that disregards constant factors. Namely, we characterize the running time of an algorithm by using functions that map the size of the input n to values that correspond to the main factor that determines the growth rate of n in terms of n. This approach allows us to focus on the big picture aspects of an algorithm's running time. Algorithm array max a n. We're basing it on the in terms of n. Okay, so this allows you to focus on the big picture of an algorithm's running time. So in this algorithm array max a n, given an input, an array a storing n is greater than or equal to 1 integers, we're outputting the maximum element in array. So what they're doing here, they're taking the current number, current max at the, saying that's the maximum at the value 0, then they're looping it from 1 to the n minus 1, and they're checking if it's less than it. If they are, then they're setting the maximum equal to the value. Okay. Wait, hold up. Why are they doing? Oh, yeah. Wait, this doesn't how does this? Wait, hold up. What? Oh, okay, yeah. So this returns the maximum element a. Why? Because current max is, they're assuming that the first value is the smallest element in the array. Okay? The first value is the smallest element in the array. So then if you loop through it, because it's the smallest element, every other element is greater than it. So they're assuming at the end of the array, that whatever value that's greater than it will be set to current max. So that's why this algorithm works and returns an array maximum of n integers. Big O notation, left f of n and g of n be functions mapping non-negative integers to real numbers. We say that f of n is O of g of n if there's a constant c greater than 0 and an integer constant n and naught is greater than or equal to 1, such that f of n is less than or equal to c times g of n for n is greater than or equal to n naught. What does this mean? They're just saying that if a function is less than another function, if it's less than another function, if you can multiply that function by the constant, okay? That's all they're saying. For a constant, like think about it. If you have a of two functions, like f of x is equal to x and f of x equals to 2x, right? F of x equal It is sometimes pronounced as big O of g of n. Alternatively, you could say that fn is an order of g of n. Big O notation. The function fn is O of g of n, since f of n is less than or equal to c times g of n when n is greater than or equal to n naught. Alright, here's the justification. What are they doing here? Okay, the function of an minus 2 is O of n. Okay, yeah. So, by the O of n definition, we need to find a constant c that's greater than 0, an integer constant n naught is greater than 0, k greater than or equal to 1, such that a n minus 2 is less than or equal to c of n for every integer n greater than or equal to n naught. So it is easy to say that the choice is c equal to 8 and n naught equal to 1. This is one of the infinitely many choices available because any real integer greater than or equal to 8 works for the value c, and any integer greater than or equal to 1 works for n naught. So they're just creating a function of c that is greater than a n minus 2. That's all they're saying. They're trying to create a function that is c of n that is greater than or equal to a n minus 2, and that's why they say any real number greater than 8 works. That's what they're saying here. And any number greater than equal to 1 here works. That's what they're saying. Okay, big O notation allows us to say that a function fn is less than or equal to another function g of n up to a constant factor in an asymptotic sense as n grows infinitely. This ability comes from the fact that the definition uses less than or equal to compare fn to g of n times a constant c for the asymptotic cases when n is greater than or equal to n times n naught. Alright, the big O notation is, let's characterize running times using the big O notation. Big O notation is used widely to characterize running times in space bounds in terms of some parameter n, which varies from problem to problem, but is always defined as a chosen measure of the size of the problem. For example, if we are interested in finding the largest element in an array of integers, so as in the array max algorithm, we should let n be the number of elements in the array. Using the big O, we can write the following mathematically precise statement on the running time of algorithm array max for any computer. So the algorithm array max for computing the maximum element in an array of n integers runs O of n time the number, here's the justification, the number of primitive operations executed by the algorithm array max in each iteration is constant. Why? Because it depends on the machine, right? So, hence, since each primitive operation runs in constant time, we can say that the running time of an algorithm array max on an input size n is at most a constant times n. That is, we can conclude that the running time of an algorithm array max is O of n, because it's at most a constant times n. Okay, that's what they're saying. Array max is O of n because it runs in O of n time. Alright, so some properties of big O notation. Big O notation allows us to ignore constant factors in lower orders and focus on the main components of a function that affects its growth. I'm guessing. Okay, so here, given this function 5n to the 4th plus 3n to the 3rd plus 2n to the 2nd plus 4n plus 1 is O of n to the 4th. When we say big O notation, this represents the worst case scenario, okay? So we ignore all the other ones. Note that 5n to the 4 plus 3n cubed plus 2n squared plus 4n plus 1 is less than or equal to 5 plus 3 plus 2 to plus 4 plus 1 times n to the 4th, which is a constant of n to the 4th, where c is equal to 15 when n is greater than or equal to n naught is equal to 1. Okay, so this is saying this is less than this term when you add them all times n to the 4th. Okay, that's what they're saying. So we could characterize the algorithm growth of any polynomial function. If f of n is a polynomial of degree d, that is, f of n is equal to a naught plus a1n plus all the way up to ad times d to the times n to the power of d, and ad is greater than 0, then f of n is O of n to the d power. Note that for n is greater than 1, we can have n1 is less than or equal to 1, yeah, wasn't less than or equal to n, less than or equal to n squared less than or equal to nd. Okay, hence a naught plus a1 times n plus a2 times n squared is less than or equal to adding them all up basically saying that if you add up all the exponents, not exponents, all the coefficients of any equation, right, it is always less than or equal. No, my bad. Okay. So what does this mean? This is basically saying if you take any equation, right, and then you add up all the coefficients of that equation multiplied by the last power, right, n to the last power, the highest power, it is always going to be greater than or equal than the original equation. That's all what they're saying. If you add up all the coefficients and you then multiply it by the n to the last power, it's always going to be greater than or equal than the original equation, and that makes sense. Okay, makes sense based on what we saw before. Based on this equation, it makes sense. Okay, if you think about it intuitively, because when you add up, it's mainly because if you add up all these coefficients, right, it's going to be greater than the last coefficient multiplied by for the highest power for the last equation. So that's why this is always going to be greater than this, and it will trump this value for this last power equation. Therefore, you could show that f of n is O of n to the d by redefining c is equal to a0 plus a1 plus all the way up to ad, and n naught is equal to 1. Thus, the highest degree term in a polynomial is the term that determines the asymptotic growth rate of the polynomial. We consider some additional properties of the big O notation in the exercise. Let us continue other examples focusing on combinations using algorithm design. So why is that? Basically, big O is representing the worst case scenario for any algorithm. That's why we're only caring about the worst case scenario. Alright? That's why we're caring about the algorithm for that. Alright, so here, 5n squared plus 3n log n plus 2n plus 5 is O of n squared. Why? Because we're only caring about the worst case scenario of this. This justification is that 5n squared plus this, the equation is less than or equal to 5 plus 3 plus 2 plus 5 n squared, which is equal to cn squared, for c equal 15 when n is greater than or equal to n naught is equal to 2. I kind of don't understand what n naught is in this case. Yeah, I don't understand n. Oh, is n naught the exponent? Yeah, I don't get what n naught means in this case. If you guys understand what n naught means, please tell me, because I don't understand what n naught means in this case. Alright, here's another example. 20n cubed plus 10n log n plus 5 is O of n cubed. Why? Because 20n cubed plus 10n log n plus 5 is less than or equal to 35n cubed for when n is greater than or equal to 1. Where did they get this? Where did they get this one? Oh, okay, so they got n log n is 0 for n is equal to 1. That's why they got 2 from that here. Yeah, that's why. So that's what they say n is greater than 1 here. Because n log n of 1 is 0. That's why. Oh, okay. That makes sense. Because when it's greater than or equal to 1, this is not 0. Right? So that's why this trumps it. That's why they say it's greater than or equal to 1. Okay. 3 log of n plus 2 is O log n. Justification is because 3 log n plus 2 is less than or equal to 5 log n. They're adding this with this, and then they're multiplying it by this highest power, highest function, for n is greater than or equal to 2. Okay, note that the log n is 0 for n equal to 1. That's why we use n is greater than or equal to n not equal to 2 in this case. Yeah, that's the reason why. They say greater than or equal to 2 because n equals 1. For n is equal to 1, it's 0 in this case. Alright, justification. 2 to the n plus 2 is O of n of 2 of n. Justification. 2 to the n plus 2 is equal to 2 to the n times 2 to the n, which is equal to 4 times 2 to the n. Hence hence we could take out 4 and not in this case. And not equal to 1 in this case. Okay. 2 to the n plus 100 log n is O of n. 2n plus 100 log n is less than or equal to 2 plus 100 times n. Oh, okay, they're multiplying by the highest value, that function that trumps this, which is n. As we saw in the previous examples, that n is always going to be n trumps n log n, because n is the worst case scenario. We're talking about worst case. O of n is worst case scenario, right? So because n grows faster than log of n, we consider n here. Okay, so that's why less than or equal to 100 n 2 times n, for n is greater than or equal to n naught, which is equal to 2. Hence we could take c equals to 102 in this case. Alright, in general we could characterize functions in this most simplest terms. Okay, as closely as possible. So when it's true that the function f of n is equal to 4n cubed plus 3n squared is O of n to the 5th, or even O of n to 4, is more accurate to say is O of n to 3. So what they're saying is, technically you could say that you could raise a function as high as it possibly can, but it's actually way better to consider of saying O of n 3. The reason they do this is if a traveler just driving along a country road happens to stumble on a local farmer walking from a supermarket. If the traveler asks the farmer how much longer he must drive before he could find food, it may be truthful for the farmer to say certainly no longer than 12 hours, but it's much more accurate and helpful for him to say he can find a market just a few minutes to drive up this road. Thus, with the big O notation, we should just drive as much as possible to tell the whole truth. Alright, so what does this mean? This paragraph is just saying that you want your equation for your O of n, big O of n, right, to be as truth as possible, okay? As close to the actual function as possible. Because if you say anything like larger, like in this case of the farmer saying the drive will take no longer than 12 hours, that's not going to help people at all. It's more accurate to say it will take a few minutes to drive up the road. That's the reason why we say big O notation. You want to tell as much possible to tell the truth. Alright, it's also considered poor taste to include constant factors and lower order terms in big O notation. For example, it is not fashionable to say that the function 2n squared is O of 4n squared plus 6n log n. Although this is completely correct, we should strive instead to describe the function in the big O in simplest terms. The 7 functions used in section 4.1 are the most common functions used in conjunction with the big O notation to characterize the running time and space usage of algorithms. Indeed, we typically use the names of these functions to refer to the running times of the algorithms they characterize. So for example, we would say that an algorithm that runs in the worst case time 4n squared plus n log n is quadratic time algorithm, since it runs in O of n squared time. Likewise, an algorithm running in time at most 5n plus 20 log n plus 4 would be linear time algorithm. Okay. Alright, let's talk about big omega. Just as big O provides of a asymptotic way of saying that a function is less than or equal to another function, the following notation provides a asymptotic way of saying that a function grows at a rate that's greater than or equal to another. So let's say f of n and g of n be function mapping non-negative integers to real and linear numbers. We say that f of n is big omega of g of n. Pronounced f of n is big omega of g of n if g of n is O of f of n. That is to say there's a constant c that's greater than 0 and an integer of constant n naught that greater than or equal 1, such that f of n is greater than or equal to c of g of n for n is greater than or equal n naught. This definition allows us to asymptotically say that one function is greater than or equal to another function to a constant value. So what does this mean? It's just basically saying that you could have a notation providing a way that a function grows at a rate that is greater than or equal to another. That's what it's saying. Big omega is saying that this function 3n times log of n plus 2n is big omega of n log n. What is that saying? That you could have a constant multiplied by n log n. That's what big omega means. So 3n log n plus 2n is greater than or equal to a constant 3 times n log n. That's what this big omega is saying. Is that whatever equation you have is equal to a constant times whatever function it is. That's what a big omega means. That's what they're saying. Okay. Now let's talk about big theta. In addition, there's a notation that allows us to say that two functions grow at the same rate up to constant values. We say that fn is big theta of g of n if f of n is O of g of n and fn is big theta of g of n. That is, there are real constants c and c prime and c double prime greater than 0 and a integer constant n not greater than or equal to 1, such that c prime of gn is less than or equal to f of n, which is less than or equal to c prime double prime gn multiply for n is greater than or equal to n naught. So what does this mean? This is basically saying that two functions grow at the same rate for constant values. Okay, so if you say that there's this function, let's say you have this function 3n log n plus 4n plus 5 log n is big theta of n log n. What does that mean? That basically means that if you take this number, whatever function is, right, that is big theta of, right, you can multiply it by a constant, and it's going to be less than or equal than your function, but it's going to be but your function is going to be less than or equal to 3 plus 4 plus 5, which is the adding up all the coefficients together, multiplied by n log n, multiplied by your worst function, for n is greater than or equal to. This basically allows us to say that two functions grow at the same rate up to constant value factors. They're saying that the big theta is something is big theta of another thing if that thing is O of g of n and f is big theta big omega, right? So something big theta of it is if f of n is O of g of n and f of n is omega g of n. That is, there are real constants such that they're constants of your original function multiplied by another function that is also less than or equal to another constant multiplied by another function. That's all they're saying here. That's what they're saying here, okay? Is that you could bound something by a constant multiplied by a function. It's always less than or equal to your original function, which is less than or equal to another constant bounded by this same function. So here they took n log n and they bounded it by n log n for both sides, and they're saying this function is always going to be between 3 and the maximum, the big theta, not big theta, O of n for it, by adding up all the coefficients together multiplied by the highest n log n function. That's all they're saying here, okay? Well, let's talk about asymptotic analysis. So suppose two algorithms solving the same problem are available. An algorithm A, which is running time O of n, and algorithm B, which is running time of O of n squared. Which algorithm is better? We know that n is O of n squared, which implies that the algorithm A is asymptotically better than algorithm B. Although for a small value of n, B may have a lower running time than A. We can use the big O notation in order of classes of functions by asymptotic growth rate. Our 7 functions are here are ordered by increasing growth rates here. So if a function precedes the other function, that means it's less than it. Okay, it's just all the growth rates, alright, and each one is less than the other. We're just showing them that which algorithm is better, which function, which growth rate is better for each of these functions. That's what we're saying here, okay? Alright, so here they demonstrate the growth rates of all the 7 functions. We assume the importance of the asymptotic viewpoint In this case, it shows the maximum size for an input integer that is processed by an algorithm is 1 second. Alright. 1 minute and 1 hour. It shows the importance of good algorithm design because an asymptotic slow algorithm is beaten in long run by an asymptotic faster algorithm, even if the constant factor for the asymptotic faster algorithm is worse. See, the importance of good algorithm design goes beyond what can be self-effectively given a computer. Even if we achieve a dramatically speed in hardware, we cannot overcome the handicap of a slow algorithm. That's what they're showing here. Alright, let's use the big O notation. So having made the case of using the big O notation for analyzing algorithms, let us briefly discuss a few issues concerning its use. It is considered poor taste in general to say f of n is big O less than or equal to big O of g of n, since big O already determined denotes less than or equal to concept. Likewise, although common, it is not fully correct to say f of n is equal to O of g of n with understanding the equal sign, since there is no way to make this sense of the statement O of g of n is equal to f of n. In addition, it is completely wrong to say f of n is greater than or equal to O of g of n, or f of n is greater than O of g of n, since g of n have an upper bound on f of n. It is best to say f of n is O of g of n is O of g of n. So they're just telling us the best way to say it, okay? That's all this paragraph is saying. The best way to say is f of n is O of g of n, okay? For more mathematical inclined, it's correct to say f of n is I think this means element. This is an element of O of g of n, okay? Big O notation is technically speaking denoting a whole collection of functions. In this book, we stick to presenting big O statements as f of n is O of g of n, okay? Even with this interpretation, there is a considerable freedom in how we use arithmetic operations with the big O notation, and with this freedom comes a certain amount of responsibility. Okay, so some words of caution. A few words of caution that asymptotic notation are in order at this point. The first note is that the use of big O in related notations can be somewhat misleading should the constant factors they hide be very large. For example, while it is true that say a function 10 to the 100 power n is O of n, if this is the running time of an algorithm being compared to a running time whose running time is 10 n log of n, we prefer to say n log n, okay? Time algorithm, even though the linear time is asymptotically faster. This is preference because the constant factor c 10 to the 1 Google is believed by many astronomers to be the upper bound of the number of atoms in the observable universe. So we are unlikely to ever have a real world problem that has this number as its input size. Thus, even if when using the big O notation, we should at least be somewhat mindful of the constant factors and lower order terms that are hiding. So this is what they're saying in this paragraph. They're just saying there might be terms that are hiding of constant values and lower order terms that are hiding in whatever algorithm that you're analyzing. That's what they're saying, okay? The observation above raises the issue of what constitutes a fast algorithm. Generally speaking, in any algorithm running of O of n log n time with a reasonable constant factor should be considered inefficient. Even an n square time method may be fast enough in some contexts. That is when n is small, but an algorithm running in O of n 2 to the n time should almost never be considered inefficient. Okay, so let's look at did I skip a page? Okay, let's look at exponential running times. So there's a famous story about an inventor of the game of chess. He asked only for a king to pay him 1 grain of rice for the first square on the board, and 2 grains of rice for the second, and 4 grains of rice for the fourth, and 8 for the fourth. So on. It is an interesting test of programming skills to write a program to compute exactly the number of grains of rice the king would have liked to pay for it. In fact, any C++ program written to compute this number in a single integer causes an integer overflow, because a machine probably won't, the runtime machine would cause a problem. So if you draw a line between efficient and inefficient algorithms, therefore it is natural to make this distinction be that between those algorithms running in polynomial time, those running in exponential time. That is to make the distinction between algorithms with a running time that is O of n to the c for some constant c greater than 0, and those with a running time O of b to the n for some constant b. Okay, like many notations we have discussed in this section, this would be taken with a grain of salt for an algorithm running n to the 100 time polynomial, probably not be considered efficient. distinction between polynomial time and exponential time is characterized by robust tractability. All they're saying is just to take it with a grain of salt, okay? Just take it with a grain of salt, okay? You might have to, if you have to draw a line between two algorithms, you have to draw a line, okay? Summarize the asymptotic notation of big O and big theta provide a convenient language for us to analyze data structures and algorithms. As mentioned earlier, this notation provides convenience because they let us concentrate on the big picture rather than the lower level details. Our two examples of asymptotic algorithm analysis. We conclude this section by analyzing two algorithms that solve the same problem, but rather different running times. The problem we are interested in is that one of the computing so-called prefix averages of the sequence of numbers, namely, given an array x storing n integers, we want to compute an array A such that A of I is the average of all the elements. Okay, so all they're doing is they're trying to compute the average of all the elements. So to compute prefix averages, alright, these are just applications. Likewise, given a stream. Okay. So we just want to average. We just want to compute all the average of all the numbers in this array. That's all we're trying to do. Okay. So how do we do it? Well, you could have a quadratic time algorithm. Your first algorithm in the prefix average problem, call it prefix averages 1, is shown in the code. It computes every element of A separately, followed by the definition. So here's how it does it. Given this prefix, an array x of numbers, input array x numbers, an element array of numbers such that A of 1 is the average of the elements. You want to output an average, so what they're doing is they're going to loop through it, right? To get a number A, they're going to loop through it, and they're going to add up all the values of A, and then they're going to divide it by the total number of values, and then return A. This algorithm is quadratic because there's two loops, right? So what they're doing is they're just summing up, they're looping through the whole array, right? And then they're summing up all the values, and then they set whatever the array to equal the average of the values. They divide it by the I to give you the average of it, and then they return the A. That's what they're doing here. So they're going to analyze this. So initializing and returning an array A at the beginning and end can be done with a constant number of primitive operations per element and takes O of n time. There are two nested for loops that are controlled by counters I and J, respectively. The body of the outer loop controlled by counter I is executed n times for I is equal to 0 up to n minus 1. Thus the statements A equals 0 and A at I and A over AI plus 1 are executing n times each. This implies that these two statements plus the incrementing counting of I contribute a number of primitive operations proportional and that is O of n time. The body of the inner loop, which is controlled by counter J, is executed I plus 1 times, depending on the current value of the outer loop counter I. Thus the statement A equals A plus X of J in the inner loop is executed n times. So that's why the inner loop contributes O of n squared time. A similar argument can be done with the primitive operations associated with the incrementing and testing counter J, which takes O of n squared time. The running time of an algorithm prefix averages is given by the sum of three terms. The first, the second are O of n, and the third term is O of n squared. By a simple application, the running time of the prefix averages is O of n squared. Okay, so now we're going to try to do it linearly. Okay, in order to compute the prefix averages more efficiently, we observe that two consecutive averages are similar. Yeah, A of I. Whoa, I didn't even know that. Okay. Given A of I minus 1 is equal to the average, right? But then the next term, A of I, is equal to that same average. This is the same average. These values are the same. Do you see it? Plus, you just add a new term. Okay? So you note that these are similar, and the averages are similar, okay? So if you denote with SI, the prefix sum x0, x1 plus up to xi, you can compute the prefix averages of AI equals S1 over I plus 1. It is easy to keep track of the current prefix sum while scanning the array with a loop. So now, what are they doing here? Because this term was repeated, right? You could actually be able to store this value that was repeated don't see it, right? So what do they do here? They loop through, given an array of n numbers, right? They want to output the average, so they loop through the value of n, and then they have an integer s represents the summing up the values, right? They sum up the prefix values, okay? And then they set I s plus equals x at I, and then they divide it by it. Well, that's genius. So what did they do? They basically summed up these values, okay, the prefix values here, as what you see up, because these values are repeated over and over again. The prefix values, this value and this value is repeated. So basically, they're just summing up that value. This just represents summing up the prefix value, which is this. Once they have this, all they have to do is set the value at I equal to this, I plus 1 divided by it, and return the value a. That's pretty cool that they are able to get an algorithm that fast. Okay. The analysis running time of algorithm prefix averages 2 follows. Initializing and returning array a at the beginning and end can be done with a constant number of primitive operations per element. It takes O of n time. Initializing variable s at the beginning takes O of 1 time. There is a single for loop which is controlled by counter I. The body of the loop executes n times for I is equal to 0 up to n minus 1. Thus the statements s equals s plus x of I and a of I equal to s over I plus 1 are executed n times each. This implies that these two statements plus the incrementing and testing of counter I contributes a number of primitive operations proportional to n, that is O of n time. Running time of this algorithm prefixes averages 2 is given by the sum of the three terms. The first and the third are O of n, and the second is O of 1. By a simple application of the proposition, the running time of the prefix algorithm is O of n, which is much better than quadratic time. Wow, that is actually really cool. The fact is that they were able to get the analysis to be O of 1 time is really cool. Okay, let's talk about recursive algorithm for computing powers. So a more interesting example of algorithm analysis, let us consider the problem of raising a number to an arbitrary non-negative integer n. That is, we wish to compute the power function x to the n, right? This function can be a immediate based on linear recursion, so x times the previous values, right? This definition leads immediately to a recursive algorithm that uses O of n function calls to compute x to n. We can compute the power function much faster than this by using an arithmetic definition based on linear recursion. Could do a square technique. Wow, that's pretty cool. Oh, okay. So if n is 0, you return 1. Otherwise, return x times x of n minus 1 over 2 squared if it's odd. If n is greater than 0, n is odd. Otherwise, you do x to the power of n over 2 squared if n is even. So how does this work? Okay, so n is even, right? To the 4 is even, right? So what they're saying is that you could do 2 to the 4 over 2, 2 to the power, 2 to the power of 4 over 2, which is right here, to the power of 4 over 2, square that, square it. What they're doing is they square it, right? That helps you get your end result. That's all they're saying. So also 2 to the 5th power, you could do 2 is equal to the 1 plus 4 over 2 times 2, which is equal to, you could do 2 times whatever power, right? 2 to the 4 minus 1, 5 minus 1 is just 4 over 2 squared. That's what they're saying here. Alright, so 2 to the 5th is equal to 2 times 2, x is 2, right? 2, so they're saying 2 to the 5th power, x is 2, 5 is n, right? 2 to the 5th power means x, 2, 5 is n. So they're saying if you want to calculate 2 to the 5th power, just multiply 2 times whatever power it is, square. 2 times 5 minus 1 is 4. 2 to the 4 divided by 2. There's 2, which is, they're saying 2 to the 5th, it could be equal to 2 times 2 to the 2nd power, 2 to the 2 power squared. Alright, that's all they're saying here. If you just substitute these numbers for x is equal to 2 and n equals to 5, you could get this power if it's odd. Alright, let's just go down. Whoops, my bad. Yeah. So this algorithm is just the algorithm of this code, which is the power of x to the n. So given a number n, x and n is greater than equal to 0, the value x to the n, if n is equal to 0, then they return 1. If x is odd, they say y is equal to, find the power, call the power x to the n minus 1 over 2. Subtract 1, right, of this power. Raise x to, call this function again, raise x to the power, instead of use n minus 1 divided by 2. Then multiply it by itself. Otherwise, you set y is equal to power x over n over 2. Return y times 1. To analyze the running time of the algorithm, we observe that each recursive call of the power function divides the exponent n by 2. Thus, there are O of log of n recursive calls, not O of n. That is by using linear recursion, the squaring technique, they reduce the time for the computation of the power function from n to log of n, which is an improvement. It divides the exponent n by 2. Oh, that's pretty cool. Okay. Alright. Some more examples of algorithm analysis. So now that we have big O for doing algorithm analysis, we're going to give more examples of simple algorithms that can have their running time characterized in this notation. So we can illustrate how each of the 7 functions given early in this chapter can be used to characterize the running time of an example algorithm. So a constant time method. To illustrate the constant time algorithm, consider the following function, which just returns the number of cells in an array. So given this array, return array.size. This is a very simple algorithm because the size of a vector is stored as a member variable in the vector object, so it only takes a constant number of time to look up and return the value. So here the capacity runs at O of 1 time. That is where the running time of this algorithm is independent. The value of n, the size of n, the array. Alright, finding the maximum number of the array. So here they coded it in C++ vector class, right? And it's supposed to find the number of maximum in the array. You could see that it compares each of the n values in the array of the first value, the current, and then to return the maximum. Thus it spends a constant amount of time for each of the n elements in the array, and as with the pseudocode version of the array maximum algorithm, the running time of the algorithm is O of n. Alright, further analysis. A more interesting question with respect with the above maximum is how many times we update the current max value. Note that this statement is executed only if we encounter a value array that's larger than it. In the worst case scenario, that you perform the test if the input array is sorted. That is the worst case. You go through all the elements, hence O of n times. But what if the input array is given in random order, with all orders equally likely? What would be the expected number of times we update the maximum element in the case? To answer the question, we update the current maximum in the ith iteration only if ith element is bigger than all the other ones preceded. But if the array is given in a random order, the probability that ith is larger than all of it is 1 over I. Hence, the expected number of times we update the maximum is 1 over I, which is known as the nth harmonic number. Therefore, the expected number of times the maximum is updated when the above maximum finding algorithms run on a random arrays log of n. Oh, that's so cool. Okay. Yeah, that's pretty cool. I didn't know that. Alright guys, let's talk about three-way set disjointness. So suppose there are 3 sets and you want to find whether or not there's an element in all of them. Okay? So if you're trying to make sure, let's say you have 3 arrays, right? You want to check if there's one value that's the same as all the rest, right? So like there's a value in every single one that it's the same, okay? And if it is the same, then you return false. Well, a simple way to do this is just loop through every single array, every single vector, right?
and checking each one to see if they're equal to one another. And if they are, then you return false. Otherwise, return true. So this simple algorithm goes through everything and checks if all of them are equal. And this is the worst case is 3n to the third. More of the worst case is achieved when the sets are disjoint, since in this case we go through all n to the third triplets of every single indices. Such a running time would generally not be very efficient, but there is a better way to solve this problem in another exercise. Okay, let's see. How much further do I have to go? Oh, okay. Let's talk about recursion, run among. So next few problems we're going to study are element uniqueness problem, which is in a range of I to j indices of an array A, which we assume is given as a STL vector. You want to determine if the elements of this range are all unique, that there is no repeated elements in a group of array entries. The first algorithm we give for solving the problem is a recursive one. It uses recursion in a very inefficient manner, as shown in the C++ implementation. It just goes through it and checks if it's unique. And then if start is equal to end, it returns true. Otherwise, if start is greater than or equal to end, return true, right? If it's not unique, then you return false. If it is unique, if it's not unique, return false. They're just checking if the value at start is not equal to the value at end. And all they're doing is incrementing start and decrementing end, right? So you should convince yourself that the function is correct. To analyze this recursive algorithm, let's determine how much time we spent outside of recursive calls and any invocation of the function. No, there are no loops, right? So here's a problem. How do you do the recursive call of the function that has no loops? Well, the non-recursive part of the function runs in constant time, that is O of n. Hence, to determine the worst case time, we only need to determine the worst case, the total number of calls it takes to make it to its unique function. So n is the number of elements in the array, right? So that is let n is the number of elements under consideration. So let n equal to end minus 1, start plus 1. So if n is 1, then this running time of the algorithm is O of n, since there's no recursive call. But to analyze the running time of the general case, that is unique, makes 2 recursive calls of the problems of n minus 1. Thus, in the worst case, a call for a range of size n makes 2 calls on ranges of size n minus 1, which each makes 2 calls on ranges of size n minus 2. Each of these makes 2 calls on ranges of size n minus 3. Thus, the worst possible outcome for the worst case for the total number of function calls is summing up 1 plus 2 plus 4 plus 8 plus all the way up to 2 to the n minus 1, because it makes 2 calls on each range of n minus 1. So, which is equal to 2 to the n minus 1 by proposition. That's the worst case running time of the function is O of 2 to the n. This is incredibly inefficient for solving the element uniqueness problem. Its inefficiency comes not from the fact that it uses recursion, it comes from the fact that it uses recursion poorly. Okay, here's how you do it iteratively. So a better way to do it is doing iteratively. So all they're doing is looping through every single element, and then looping through the second element, checking if they're equal. If they're equal, then return false. Okay, this solves the element uniqueness problem, looping through all the distinct indices I and j and checking if any of them are a pair that are equal to each other. It does this using 2 nested for loops. One does n minus 1 iterations of the inner loop, and the other one does n minus 2 iterations of the inner loop. The third one does n minus 3 iterations of the inner loop, and so on. Thus, the worst case scenario is n minus 2 is adding them 1 plus 2 plus 3 plus 4 up to n minus 1. So, alright guys, so now it's in the afternoon and it's not the morning anymore, so I could talk normally. I don't have to whisper anymore. So let's talk about using sorting as a problem solving tool. An even better algorithm for the element uniqueness problem is based on using sorting as a problem solving tool. In this case, sorting the elements, we could guarantee that any duplicate elements will be placed next to each other. Thus, when you sort the array and look for duplicates among the consecutive elements, this is what happens. Look what happens. So it makes it more efficient. Why? Because look, if start is greater than or equal to n, right, return true. But then they have the buffer of the array, right? Now, if you sort it, you could just have to check if the element is right next to each other. Then you could easily check for duplicates. And this function sort provided by this is a function sort provided by STL. In most systems, it runs n log n. Since other steps run in O of n time, the entire algorithm runs in O of n log n. So we can solve the element uniqueness problem even faster, at least in terms of average case scenario, by using a hash table, which we'll do it in 9.2. Alright, so let's talk about justification techniques. And this is just a way to, when you make claims about algorithm, you can show that is correct and that it runs fast. In order to rigorously make such claims, you must use some mathematical language. In order to do that, you have to justify or prove our statements. So there's a few ways to do this. You could do this by example. So some claims are just generic. There's an element x in set S that has a property P. To justify it, you just have to produce a particular S in S that has a property P. Likewise, some hard to believe claims are of the generic form: every element x in a set S has a property P. To justify that such an element is false, we just have to produce a particular x from S that does not have property P, and such is called a counterexample. So for example, the Professor Amagas claims that every number from the form 2i minus 1 is prime when I is an integer greater than 1. So it's wrong, because you could prove him wrong by finding a counterexample. And you just say 2 to the 4th minus 1 equals 15, which is equal to 3 times 5. And that's not a number that has a form of 2i minus 1 where it's a prime, right? That's not a number, so that's why he's wrong. Or the contra attack. So another set of justification techniques involve using the negative. So the two primary such methods are using contrapositive and contradiction. The use of contrapositive is like looking through a negative mirror. To justify the statement, if P is true, then Q is true, we establish that if Q is not true, then P is not true instead. Logically, these two statements are the same, which is called the contrapositive, and it may be easier to think about. So let A and B be integers. If A, B is even, then A is even or B is even. To justify this claim, consider the contrapositive. If A is odd and B is odd, then AB is odd. So suppose A is equal to 2i plus 1 and B equals to 2j plus 1. For some integers I and j, then AB is equal to 4ij plus 2i plus 2j plus 1. Hence, AB is odd. So basically, they're just saying that if you prove by contradiction, prove the statement is wrong. Not the statement is wrong. For proving contrapositive is basically just saying that so let's say if AB is even, right, then A is even or B is even. So you just say the negative. Well, if A is odd, so so the negative is just saying if A is odd. Well, it's just saying if A is not even, which means A is odd, and B is odd, which is then AB is odd. And if you create an example for that, you prove that the statement is true. All right, because if you prove the contrapositive is just the opposite, right? So if P is Q, then Q is true, right? You just have to make sure prove that if Q is not true, then P is not true, and that basically proves your statement. If P is true, then Q is true. Okay. So besides showing a use of contrapositive, a justification technique, the previous example also contains the application of De Morgan's law. De Morgan's law helps us deal with negatives. So for it states that the negation of the statement of the form P or Q is not P and not Q. So if you do the negation of P or Q, it's not P and not Q. Okay. Like if it's not apples or oranges. Okay, so negation of apples or oranges is not apples and not oranges. All right. Well, I want apples or, so if you say, let's think about it this way. When you ask someone, do you want apples or oranges? For the negation of this statement will be, I do not want apples and I don't want oranges. That's a negation. See, it makes it easier to understand, right? Just think about it in terms of apples and oranges. The negation of P or Q is not P and not Q. Likewise, it states that the negation of a statement of the form P and Q is not P or not Q. So, do you want apples and oranges? No, I do not. I don't want apples and I don't want oranges. I don't want apples or oranges. That's what it means, right? That's what it stands. All right, contradiction. Another negative technique is called justified by contradiction, which involves using De Morgan's law. So if applying the justification by contradiction technique, we establish that a statement Q is true by first supposing that Q is false and then showing that this assumption leads to contradiction. So you could assume that it is true, that if you want to say that Q is true, you first assume it's false and that it goes impossible. It's like it just doesn't work, right? So by reaching such a contradiction, we show that no consistent situation exists with Q being false, and so Q must be true. So you first have to assume this situation consistent before you can do that. So let's say A and B are integers. If AB is odd, then A is odd and B is odd. If you want to prove this using contradiction, you say, okay, let's assume that AB is odd. Okay, we have to show that A is odd and B is odd. Well, so with the hope of leading to a contradiction. So let's assume that what they're saying is true. Okay, so suppose A is even or B is even. Okay, now let's assume the opposite is true, actually. Let's assume the opposite is true. So suppose A is even or B is even. So in fact, without loss of generality, we can assume that A is even. Hence the same case for B is even, right? Then A is equal to 2i for some integer I because of this is because of definition of even integers, right? The definition of even integers means that you could represent it as 2 times some number, right? That's just the definition of even integers. Hence, AB is equal to 2i times B, which equal to 2ib, right? Because you could represent A as 2 times another integer I, right? So that's why AB is equal to 2i times B, which is equal to 2 times IB. That is AB is even. But this is a contradiction. AB cannot be even and odd. Therefore, A is odd and B is odd. So, let me explain this again. So, if you want to show something by contradiction, you have to assume the opposite is true, and it leads to a contradiction, right? So, we were trying to prove that let A, B be integers. If AB is odd, then A is odd and B is odd, right? Now, let's assume that for the sake of contradiction, right, the A is even and B is even, right? So if A is even and B is even, and then we assume that this is true, then AB should be if A is even and B is even, right? If you assume the opposite is true, and you leave to a contradiction, then the thing is it can't be both. It leads to a contradiction. Therefore, that is false, and then your original statement is true. That's what proving by contradiction means. So So let me just explain it again. So let A be. So A and B are integers, right? If AB is odd, then A is odd and B is odd, right? I'm guessing we're trying to prove this, right? So how they did it, they let AB be odd, right? So AB is odd, right? They want to show that A is odd and B is odd, right? So with the hope of leading to a contradiction, they assume the opposite is true. So suppose A is even and B is even. So this is A is even and B is even. So based on this, they saw that if you multiply them together, it's even. But therefore, but you can't be even and odd. Therefore, this leads to a contradiction. So therefore, A is odd and B is odd. So therefore, they prove this statement true, because they assumed the negation is true, and then but it led to a contradiction. So that's why it's proved by contradiction. So yeah, therefore the original statement must be true. That's what they're saying. Okay, let's talk about induction and loop invariants. So a lot of claims about running time or a space bound involve a integer parameter n denoting the size of the problem. Most of these claims are equivalent to saying that some statement q of n is true for all n is greater than 1. This is making a claim about infinite number of numbers, so we cannot really justify this claim in a direct fashion. So some justification techniques, you could do it by induction, right? So how do you do by induction? You could often justify claims such as those are true by using a technique called induction. This technique amounts to showing that for any particular n is greater than 1, there is a finite sequence of implications that start with something known as to be true, then leading to showing that q of n is true. So specifically, we begin a induction by showing that q of n is true for all n is equal to 1. Okay? And Then we justify that the inductive statement is true for n is greater than k. And then we show that if q of I is true for I is less than n, then q of n is true. Any of these combinations will do by induction. I don't that was a horrible explanation of induction. Okay, really, what induction is basically, in order to show something is true for an infinite amount of things, you have to just show that it's like dominoes. Like, think about it as terms of dominoes, right? You have to say you have to assume that this is true for one case, and that then the k plus one, the next case, is true as well, and that's going to cause a domino effect. That's what it basically is. So here, let's show you an example. So here, let's say we have a Fibonacci function f of n, where we define f of 1 is equal to 1 and f of 2 equals to 2, and then the function is this, right? For n is greater than 2. We claim that f of n is less than 2 to the n. Well, you could do this by induction. So what do? You first say that, okay, in our base case, n is less than or equal to 2, right? F of 1 is equal to 1, and f of 1, you show that the first case is true, okay? So what I told you about the domino effect. Show the first case is true. So this is just showing that this is true, right? For this particular case is true. And so that's what they do here. They want to say that f of n is less than 2 to n, right? For when it goes infinity, right? So what do? So they say, okay, we'll start with f of 1. Well, f of 1 is less than 2 to the n. To the n, right? If you do f of 1, you get 1, and it's less than 2 to the n. To the n is to the 1 is 2. That's what they do here. Okay? That's what this f of 1 is equal to 1, which is less than 2 to the n. So that this proved that f of 1 is true. Okay? So they're trying to prove that f of n is less than 2 to the n, right? So in order to do that, we first have to say, okay, we have to prove the first domino is true. So for this case, first domino has to be true for the first case, right? So the first case, f of 1, right? And that's less than f of 1. 1 is less than 2 to the n, right? Because when you plug in 1 for 2 to the n, you get 2, right? And 1 is less than 2, which is why f of 1 is less than 2 to the n for this part. So that showed that this is true for f of 1. Now we're going to show that it's true for f of 2 as well. So we plug in 2 for f, and we get what? So based on what they gave us for the Fibonacci sequence, f of 2 is 2, right? Now we plug in 2 for 2 to the n as well. So 2 to the n is 4, right? So that proved 2 is less than 4. So that showed that our first case is true, which is our base case, the first case, when f of is 1 and f is 2, right? But we are trying to prove that that for all the cases for greater than f of n is less than 2 to the n. So we proved the first two cases, based on the facts that they gave us, that f of 1 is 1 and f of 2 is 2, right? And we plugged it into this to show that it's true, and it is true. Now, suppose our claim is true for n prime, which is less than n. So for the next numbers, that's basically what it's saying. Suppose it's true for the next numbers, right? So since n is greater than 2, we get f of n is equal to f of n minus 1 plus f of n minus 2, right? Since n minus 1 is less than n, okay? n minus 1 is less than n, and n minus 2 is less than n, we can apply inductive assumption, called inductive hypothesis, to imply that f of n is less than 2 to the n minus 1 plus 2 to the n minus 2, okay? This is, they basically skipped it. So basically, they're basically just stating that the next element is true, right? So they're trying to prove that the next element is true. So moreover, since n minus 1, which is this is n minus 1, right, is less than n, and n minus 2 is less than n, you can apply the inductive assumption to imply that f of n is less than 2 to the n minus 1 plus 2 to the n minus 2. Okay? Why? Because think about it. If I want to prove the next assumption, right? The next values. I want to prove the next values, right? Prove that n minus 1 is plus f of n minus 2. I have to show that this works for the next value. And that's what they do. They show that for the next value of this, that this value is going to be less than 2 to the n, right? 2 to the n minus 1, right, is less than, wait, hold up. Okay. So here's what they're doing. They're basically comparing the exponent currently, right? So over here they said, suppose our claim works for all the values up to less than n, right? So now since n is greater than 2, this is the function, right? This is the function that they gave us for n is greater than 2. Because since we know that n minus 1 is less than n, which by a fact, we know that this exponent, which is n, is going to be less than this whatever function here, right? And n minus 2 is less than n. You could apply the inductive hypothesis, which is that to imply that f of n is less than 2 to the n minus 1 plus 2 to the n minus 2. So what did they do? They basically just substituted n minus 1 into n. Okay? This is what they did. They substitute n minus 1 into n. Okay? And then after that, they're like, okay, since we know that n minus 1 is less than n, when we substitute it for n, in this case, we know that 2 to the n minus 1 plus 2 to the n minus 2 must be greater than f of n, right? Because assuming that this is true, that f of n is less than 2 to the n. So by substituting the next value, once we assume that this is true, right? Suppose that the claim is true. Once we assume this, we just have to prove that the next value is true. So once that this value, we prove that this is true, right? Like the domino effect. Now we have to prove that once I hit the next domino, it's going to be true as well. Okay? Like, I have to prove that for every domino right next to me that it's also true. So that's why they're saying we're assuming it works for all dominoes. Now if we prove that the domino right after us, whenever time we have a domino right after us, that is true also, then we'll be able to get it to work. That's what it's basically saying. So here, assuming that f of n is less than 2 to the n. Here, suppose our claim is true, right? That f of n is less than 2 to the n. Since n is greater than 2, right? And this is the statement they gave us. Since n minus 1 is less than n, right? And n minus 2 is less than n. Plugging these in, you get this, right? You get f of n, which is less than 2 to the n minus 1 plus 2 to the n minus 2, right? Because this has to be greater than f of n. Because after even if you plug n minus 1 into this equation, it still has to be greater than f of n, right? Because think about it. We're assuming that this is true. The f of n is less than 2 to the n, right? And because we know it's true, well, you know that n minus 1 is less than n, right? So if you plug it in and you add it to 2 to the n minus 2, which is the second value of this, you know that it has to be greater than f of n. And since this is less than 2 to the n minus 1 plus 2 to the n minus 2 is less than 2 to the n minus 1 plus 2 to the n minus 1, that equals to 2 times 2 to the n minus 1, which is equal to 2 to the n. And so because of this, you could prove that f of n is less than 2 to the n. Okay? I might not be explaining this correctly, but I hope you guys understand. Okay? Okay, let's do the second value. Okay, let's do another example. So you could do, okay, so suppose we have this. that I is equal to n times n plus 1 over 2. So you could justify this by induction. So you first prove that the first case is true, where I is equal to 1. So what is I equal to 1? Well, if I equals to 1, well, that means that if this statement is true, the left-hand side has to be equal to the right-hand side, right? So for I equals to 1, well, 1 is 1 equal to 1 times 1 plus 1 times 1 plus 1 over 2? Yes. Yes, it is. If n is equal to 1. Yes. Based on this, for n equals to 1, this is true. If I plug in n equal to 1, does I equal to 1 times 1 plus 1 over 2? Does the left-hand side equal to the right-hand side? Yes, so that's true. If n is equal to 1. Now, assuming that this is true, that now for the inductive step, assuming that the claim is true for k plus 1 or the next element, right? So what does that mean? That means that based on our assumption, right, the summation of I equal to 1 to n of I is going to equal to, n, which is, where did they get n from? I'm curious. Consider n. Okay, so where did they get this from? Good example. And this is a better example that I found online. So let's say you want to prove that 1 plus 2 all the way up to n is equal to n times n plus 1 over 2, right? By induction. So what do? You first see that does it work for the first case. So you have to say that it works for the first case. So what is the first case? 1. All right. Does the summing 1 to 1 equal to 1 times 1 plus 1 over 2? All right. Does the left-hand side work for 1? And does it equal to the right-hand side? Well, yes. For n is 1, well, you're summing up to 1. So you're not summing up anything, really. So it's just 1 for the left-hand side. And that's equal to 1 times 1 plus 1, which is 2, divided by 2, which equal to 1. So that's checks. Okay. Now we assume that this works for k. For whatever number it is. Based on our claim, we assume that it works, right? So assume that it works. So you get 1 plus 2 all the way up to k equal to k times k plus 1 over 2. We're assuming it works for k. For if you substitute k for n, it works for k. Now we have to show that for the next term, k plus 1, that it works. So because we know we have to show that this k plus 1, which is the next term, equals to it's equal to the next term plus 1. So they basically took this k, right? They added up to k, but now they're adding up to k plus 1. So assuming our thing works, we have to show that it works for k plus 1, the next term after as well. So it's k plus 1 times k plus 1 plus 1, because you're substituting k plus 1 for k in our in this equation, because we're trying to find the next term, show that it works for the next term as well. So that's why they substitute k plus 1 for k here, right? So this is the next term. This is the sum of the next term, right? Now you substitute k and k plus 1 to get these lines. Notice that there he's writing out what he's trying to prove. Now you start on the left-hand side and you show basic algebra. So by basic algebra, left-hand side, this is basically equal to the equation of k plus 1 times k plus 1. So based on the inductive hypothesis, the left-hand side is this, right? Assuming it works, summing up to k, summing all the way up to k is equal to k times k plus 1 over 2. So they're substituting, so we know, because based on our assumption, we know that 1 plus 2 all the way up to k is equal to this, right? Because we're assuming that it's true. So now, based on the left-hand side, because we know, assuming that it is true, and that it is true, right? We're going to substitute this value on the right-hand side for this. Okay? So they substitute this on the right-hand side for this. Okay, so this is now gone, and now it's k times k plus 1 over 2. So it's k times, so here they have k times k plus 1 over 2 plus k plus 1, which is this, right? K plus 1. This is the left-hand side, right? Now, what is that? That equals to this, right? K plus 1. Now, based on that's by the induction hypothesis, right? Now, what about the right-hand side? So now, on this side, the right-hand side, they're trying to see what that is. Okay, so the right-hand side is, we know it's this, right? We know it's this because we're trying to prove that this works, that the right-hand side is also equal to this, right? So this is the right-hand side. So they have the right-hand side right here. So k times k plus 1 plus 2 times k plus 1 over 2, right? This is the right-hand side. So by 2 over 2 equal to 1, this is distribution over division. So they are basically going to factor. They're going to factor. So they factored this out. They factor k plus 1. They factor k plus 1 out. So they took k plus 1 from both of these sides, and they factored out for here, right? And then the k and the 2, they added them together for this part. So that the right-hand side is equal to k plus 2 times k plus 1 over 2, right? And then this is actually equal to k plus 1. If you just move the k plus 1 and you just reorder the multiplication, you get k plus 1 times k plus 2 over 2 by commutative multiplication. So once they have this, right? Well, this is basically the same thing as what we showed before from our left-hand side. Our left-hand side was this, right? If I'm not mistaken. So if you factor out the left-hand side, it is actually equal to the right-hand side. And that basically proved that this case works, that 1 plus 2 plus n is equal to n times n plus 1 over 2. You prove that this statement is true, right? Why? Because you first initially prove that the first one is true, the first statement, and then we assume that it works for all of them, right? But then that this statement is true, because we assume that we have to we prove that it works for the next element as well. So that basically showed this domino effect, and it basically proved everything works. So that's basically proof by induction. The book didn't really explain it correctly. They're just giving out random numbers and crap. I don't want to look at it. All right, let's talk about loop invariants. So a final justification technique we introduce is the loop invariant, and to prove some statement S about a loop is correct, you define S in terms of a series of smaller statements where S, like S naught and S1 up to K, as a K, where there's an initial claim, which is S naught is true before the loop begins. If Si minus 1 is true before iteration 1, then Si is true after iteration 1. And then the final statement, which is Sk implies the statement S that we wish to be true. So let us give an example of how loop invariants work to just justify corrections of algorithms. So let's just consider a loop invariant of array find, which is finding just an element in an array. So here they have an algorithm called array find, and given the input, you're given an element X and a array A. You're going to output an index such that that X exists in A, right? X is equal to A of I, right? And then -1 if there's no element inside the array that is equal to X, right? So we're just finding X in this array. So what do? Well, in this algorithm, they start I equals 0, and they're going to loop up to the length of the array, and then if it's equal to the value of X, then they return. Otherwise, they keep going to the right, and then in the end, if they never returned the index at I, then they just return -1. So to show that this algorithm is correct, you define a series of statements that lead to the correctness of the algorithm. So you first have to claim that the following is true at the beginning of the iteration of the while loop. So S of I, X is not equal to any of the first I elements of A. Is that true? This is beginning the iteration of the while loop. X is not equal to any of the first I elements of the array, right? So X is not equal to any of the first I elements of the array. So, well, what is the value of x currently, right? The first value of x is just, well, they're setting the value of x after, no, they're not setting, they're checking it inside the loop. But before the loop, beginning the iteration of the while loop, x is not equal to any of the first I elements of the array. This is true at the beginning of the iteration I of the loop, at the first I iteration of the loop, right? The claim is true at the beginning of the first iteration of the loop, since there are no elements among the first 0 in the array. This kind of trivial true is claimed to be hold vacuously. So in the I iteration, we compare the element x to the element a of I, right? So during the I iteration, you know that x is not equal to any of the first elements array, like before this if statement, right? Then during the iteration, you compare it if it's true. And if it is, you return the index if they're equal, which is clearly correct and completes the algorithm in the case. If the two elements x and I are not equal, then we have found one more element not equal to x, and we increment the value of I. Thus, the claim s of I is true for this new value of I. Hence, it is true at the beginning of the next iteration. So, it is true. So, that's why it's true on the next iteration, because they already checked if it's equal or not, right? So, if it's not equal, the next iteration, I is not going to equal a of after the next iteration, we know that x is not equal to any to the element at our position, right? After each iteration, we know definitely that x is not equal to any of the element at the iteration. Why? Because if it was, it would have returned I. So that's why before this iteration, we know that x is not equal to a of I, right? Until we've gone through here, we know, then it returns I. So that's why we know for each iteration it's not equal. Thus the claim s of I is true for the new value of I. Hence it is true at the beginning of the next iteration. If the while loop terminates without ever returning an index I, then we have I equal to n. That is, s of n is true. There are no elements of a equal to x. Therefore the algorithm correctly returns -1 to indicate that x is not an a. Alright, that was it. That was pretty much all of our justification techniques of algorithms. And yeah, hope you guys enjoyed it. Please rate, comment, subscribe, and